Section 9.4 is our last section in this chapter, right? Yes, and we're going to take a look at permutations and combinations. And before we do that, we're actually going to take a little bit of a diversion on a couple things that we're going to need in order to do permutations and combinations. So the first thing we're going to take a look at is something called a factorial. So I just want to show of hands, who has seen or heard of, I'm not going to call on you to do it, but who has seen or heard of factorials before? Okay, most of you have, not all, but most. Factorials are this notation in mathematics where you have this exclamation point. So every now and then there's, some kind of a joke on Facebook between math geeks like me, and somebody will say something like, I'm so excited, and they'll put an exclamation point after a number, and we're like, I don't mean factorial here, something silly like this, okay? Exclamation point actually means mathematically something called a factorial. All right, so let me tell you what it means when I've got any number in general. So this n right here is going to be something bigger than 1. So this is an integer. Actually, let me just say it this way. This is a natural number. And a reminder, natural numbers are the counting numbers. So we're looking at 1, 2, 3, 4, like that. Okay, so no fractions, no decimals, no negatives, nothing like that. And not even 0. We're going to define 0 differently. All right, so what does it mean to do n factorial? Well, it means to multiply out the number n, whatever it is, times the value that's 1 less than that, times the value that's 1 less than that, all the way down until you get to 3 times 2 times 1. So you're multiplying that number all the way down until you get to 1. That's what you're doing. Okay, so like 15 factorial is 15 times 14 times 13 times 2, all the way down to 1. Okay, that's the definition of factorial. 0 is not a natural number. This definition would not make any sense with 0 anyway, right? So 0 factorial, and I'll show you why when we get there, but 0 factorial by definition is the number 1. Okay, so anytime you see 0 factorial, it's kind of like saying something raised to the 0 power, 1. And again, there's a reason for it, but it'll make sense in context a lot better than right now. Okay? 0 factorial is 1. So we're going to practice one. I'm going to let you do this first. Nothing terribly complicated. 4 factorial. I want you to do this and then turn to a neighbor and make sure that you get the same result. So what would it look like? Write it out. And then what would the value end up being after you did it? Okay, so compare across the aisle with somebody. Okay, I think everybody got it. Everybody that I heard say something said 24. Did everybody have 24? Okay, great. So when we did this, of course, we did 4 times 3 times 2 times 1. And if we multiply those together, we get 24. Let me make one more comment while we're here, because we're going to see this happen again later where it's useful to realize this fact. This 4 factorial, well, we can write 4 times 3 times 2 times 1. If this number were really, really large, say like 100 factorial, right, you might not want to write out 100 factorial. There might be an actual reason why you'd want to stop short and write something like this. Again, it doesn't make sense for this particular one, but recognize that 4 factorial would be the same thing as 4 times 3 factorial, because 3 factorial would be the 3 times 2 times 1. So you can abbreviate a portion of it and write out a portion of it at the same time, and it actually is the same expression, just looking different. We'll use that fact when we work on a couple problems today. All right, now this one is the other thing that we're going to need in advance of being able to actually do permutations and combinations. This is called the fundamental principle of counting. And for those of you who have had what we used to call elementary math 1, you've seen this before. It's in chapter 2 of this particular textbook. And it says the following: if event capital M can occur in little m ways, and event capital N can occur in little n ways, then event M followed by event N can occur in m times n ways. And we've used this fact, it's been sort of hidden behind the scenes when we've done our multiplication on our tree diagrams. You know when we do a tree diagram and we multiply along all the branches? That's this principle, okay? We've done it for probability, but it can be done for counting ways of certain things to happen as well. And there's nothing special about the fact that this is two things that are happening. So like for instance, let's say event M is the shirts in your closet and event N is the pants in your closet. And you want to know how many outfits you have if you're going to be able to combine shirts and shorts or pants or whatever it is interchangeably. Okay, nobody said they matched. Okay, but how many could you combine? Okay, well what you do is you just multiply the number of shirts times the number of shorts. But let's throw in the mix their shoes. That's okay, then you just multiply shirts times shoes times shorts. Let's throw in their headbands. You multiply the headbands out, or whatever it is, okay? So this can be done in a multiple versions of something. It doesn't just have to be two. All right, so let's take an example of Pizza Planet. What's Pizza Planet from?
Toy Story.
Very good. Well done. One of these days, nobody's going to know anymore. I don't know how long it's going to take, but it's going to happen, you know. My son is convinced he wants to go to Pizza Planet all the time. He thinks that, you know, we're going to go to pizza, he's going to go to Pizza Planet. And I'm like, doesn't really exist. Actually, there is a Pizza Planet we found somewhere. I don't remember where I was traveling or something. But. All right, Pizza Planet. Pizza Planet has some meal deal options, so to speak. They have 3 kinds of salad, 15 kinds of pizza, and 4 desserts. So how many different meals can you make that would consist of 1 salad, 1 pizza, and 1 dessert? So what would you do?
Multiply them all together.
Yeah, you just multiply them all together. And that's the fundamental principle of counting. Okay? This is what you would do at Subway, right? If you're trying to figure out how many different sandwich combinations you could make, something like that. And you're restricting this to 1 bread, 1 meat, 1 cheese, 1 vegetable or something. All right, so we would take our 3 times 15 times 4. And if we multiply, what do we get? 180 meals. Okay, does that make sense? Okay. All right, so now we're going to actually move into this thing called permutations. Not to confuse things, but unfortunately there are 2 things called permutations. I know that's not real helpful. We'll talk about the first one, and the thing to notice about this is this phrase right here, is that the objects are like objects, things that are alike in some way. So if we have n elements, so there's 15 or there's 20 or there's 32 or there's 8, whatever it is, and some of them match other things. So an example you're going to do in your textbook is the word, they're going to have a word like the word Tallahassee. Well, some of those letters are repeated, right? So if I pick the first L instead of the second L, it doesn't look any different. You guys with me? I mean, some of these things actually match each other, so there's not a distinguishable way to consider that. So what they're saying is we've got n elements, R1 of which are alike, R2 of which are alike, and so on. So you have a bunch of things that match other things. Okay? Then if we want to know how many ways can we actually see distinguishable differences, the way that we do that is by taking n factorial and dividing it by the things that match with factorials. You know, so like the L factorial, whatever L was in Tallahassee, however many L's there were, however many H's there were, however many T's there were, however many S's there were. Okay, so write that formula down. You're going to need that one. And we're going to do an example, and we're going to do an example with candy, because I know you guys like candy. Does anybody like Starburst? Okay. So in Starbursts, there are 4 colors, the traditional Starburst ones, right? Red, orange, yellow, and pink. And the favorite one is? Pink. Oh, somebody said red. Pink's my favorite too. My sister likes red the best. Okay. So there's whenever you get one of these packages of Starburst, there's not a for sure number of any of the colors in them. I don't know if you've seen that before. But you don't really know for sure how many is going to be in there. So we've made up an example. And I don't even know if this is the number of Starburst in a package. I should have looked that up. That would have been really wise. Didn't do that. All right, so we're going to say that there's 4 red, 5 pink, 3 yellow, 2 orange. So if I eat, the first red in the package, or I eat the last red in the package, just for where they are location-wise in the package, it doesn't look any different. That's not distinguishable because it's still red. You guys see that? So this is an example of that like objects thing in that previous formula. So the first thing we have to figure out is how many elements we have. So what's that going to be in this problem? How many total starbursts I have. Very good. So how many total starbursts do I have? 14. So in this problem, my n is 14. And then the different kinds of starbursts, that's my 4 different kinds, are each one of those are with the little subscripts, right? They're the things that match each other that are alike. So we're going to do that formula. I'll write it down here. You don't have to write it down again, but just as a reminder, this is n factorial over r sub 1 factorial, and we're going to have 4 of them. So r1, r2, r3, and r4. All right, so for us, we already said that the n is 14. What in the world's going to go in my denominator? Okay, each of them is with a factorial sign after it, but yes. So 4 factorial, what do I have? 5 factorial, 3 factorial, 2 factorial. Do you have a question, Emily?
Yeah, but you keep going. I might get an answer.
Okay. Is everybody okay with what the setup is so far anyway? Okay. Now there's a couple things to notice. When we work with fractions, we do a lot of cancellations between numerators and denominators, right? Okay. When we've got factorials involved, the only cancellation we can do is if the factorials identically match. Because what you have to remember is that this 14 is not just 14. It's 14 times 13 times 12 times 11. It's a whole bunch of things, right? So if I were to cancel the 14, for instance, with the 2, and I ended up with 7 on top, that's not the same thing. I lost a lot of my factors. Now, we can do some cancellation, though, so I'm going to show you how the cancellation looks. And it is very useful to do because depending on how large your numbers are, will depend on how tolerant your calculator is of you doing a whole bunch of multiplication. Your calculator only has so many spaces wide, and then it starts turning things into scientific notation, right? And you lose accuracy. Well, we don't want it to lose accuracy. So we do want to simplify things at least to some degree before we let our calculator have a whack at it so that it doesn't lose stuff. All right? So here's what we can do. Whichever one is the largest in the denominator, and in our denominator right now, that's the number 5. We're going to write the 14 out until we get to 5, and then we're going to stop, and we're going to write 5 factorial. So it's going to look like this. 14 times 13 times 12 times 11. We're going to write a bunch of them because this one's long until it gets to the repeat part. 10, 9, not 19, 9, 8, 7, 6, and while I could write out 5, 4, 3, 2, 1, I'm going to stop and write 5 factorial. In the denominator, I have the 4 factorial. I'm going to write it out. 4, 3, 2, 1. I'm not going to write out my 5 factorial. I'm just going to write it as 5 factorial because it matches something exactly on top. So I'm going to stop that one. Then I'm going to write out my 3 times 2 times 1 and my 2 times 1. These two 5 factorials match. They are 5, 4, 3, 2, 1, all multiplied on top and on bottom, right? So we can cancel those because they represent the exact same factors all written out, 5, 4, 3, 2, 1. Now here's cool stuff. There's other things we can cancel too. There's several ways you could do it. You could just go down the list and say, oh, look, 14 and 4 have a 2 in common, divide them both by 2. You can do that. That's okay. But there are some natural things you can do that are a little bit cleaner. For example, what's 4 times 3? 12. Do I have a 12 on top? So I'm inclined to do that. Cancel the 4 times 3 with the 12. Look for things that cancel out completely instead of just reducing. Now, that doesn't work everywhere, but there is another one that works like that. 3 times 2? 6. And then you might go and do reducing. For instance, this 2 with this 14 at the beginning, that would reduce. 7 on top, nothing on bottom there, or 1 on bottom technically. And then we can do the next 2 over here with the 10 or with the 8, whichever one you like. It doesn't make any difference at all. Now here's the inherent problem with what we did. Depending on how neatly you write, and some of you write really neatly, some of you not so neatly, you might lose factors in this multiplication of stuff and canceling, right? So you need to be very, very careful of what you have left when you're working through this. I have a 7, 13, 11, 5, 9, 8, and 6. And now I really am going to, I'm sorry, 7, not 6, thank you. I really am going to take a calculator and multiply those out. Okay, that's the goal at this point. So grab your calculator. You are wanting to grab your calculator today, without a doubt. So if you don't have one, just bear with somebody who does, and you'll have their answers written down, which is cool. And once you have your answer, do the same thing. Look at a partner, see if you guys get the same number, and it's going to be big. Yes, Lauren?
I just don't understand where the numbers came from after the 5 factorial.
Yeah.
Okay. Let me see if I can highlight that for you. After the 5 factorial was a 3 factorial, right? And this piece right here is the 3 factorial written out.
Oh.
And then the 2 factorial after that has the 2 factorial written out here.
Oh.
Basically, I just attempted to write out everything that wasn't 5 factorial.
Okay.
And I mean, honestly, I could write out the 5 factorial. It wouldn't hurt anything. It's just that I don't need to because it does, in fact, match with something else.
Okay. And the 4, 3, 2, 1 is the 4 factorial.
You got it. Mm-hmm. So that's this one.
Okay. Thank you.
Aren't the color coding stuff on this pretty cool? It's one of my favorite features, actually. So, all right. What did we get? Did we get big numbers? Did you check with somebody? Did anybody check with anybody? Are we getting the same big number? Is it like 2 million something?
Yeah.
Oh, okay, good. Then you're getting what I have. So somebody tell me what big number you have. 2 comma what? Just tell me the digits.
5, 2, 2, 5, 2, 0.
522,520. Is that right, Hannah? Okay. So 2,522,520. And that was just 14 starbursts. This is the number of distinguishable ways that you could eat that package of starbursts. That seems sort of weird, doesn't it? Kind of crazy stuff. All right, did you have a question then, Emily?
Yeah. So, like, for the pizza plan example,
Mhm.
just, like, multiply them together really easily.
Yeah.
But, like, how is this problem different that you don't do?
Because on this problem, we aren't choosing a number of things. It's not like we're choosing one of the four reds and one of the 5 pinks and one of the 3 yellows and 2 of the oranges. We're eating everything.
Okay.
In the pizza planet example, we chose 1 salad, we chose 1 dessert, and we chose 1 pizza. Here, we're eating the whole package.
Okay.
Yeah. I mean, I'm eating the whole package. I don't know about you guys. Okay, just checking. All right. Here's another method, though. Okay, so this is the other permutation one. I told you there was 2. What is the difference on this one in the description at the very beginning? Unlike. Okay, so highlight, circle, mark in bold. This is the difference. This one says unlike objects. So this would be like if the starburst had every single color different. Okay? No repeats, no things that you can't distinguish between. Here again, we have n elements, like my 14 starbursts. The R tells me how many I'm choosing. So let's go back to the starburst, for example, and just pretend we had 14 different colored starbursts. Okay, but in this example, like that we didn't do, Emily, the last one I was telling you, we ate the whole package of starburst. In this example, we don't choose everything. We have the 14 starbursts, but we only eat 6 of them and we give the other 8 away, or something like that. So in this example, we have unlike objects, and we're also not choosing all of them. We're only choosing some of them. And in this one, this is important because I'll distinguish it in a minute from the next thing. The order of something matters. That is, if I eat red and then pink, it is different than eating pink and then red. Okay? The order matters for the other permutation one as well. That's exactly what we were calculating, in fact, is the number of ways that we could do something. But keep in mind this one, order matters. All right, so you see some notation here that we haven't probably seen before. It looks like subscripts on either side of a capital P. All right? Well, the capital P stands for permutation. All right, so that's why the P's there. The little n at the beginning tells me how many items you have to choose from. That would be my 14 starbursts, right? And the number R after it tells me how many I actually am choosing. In my example I just gave a moment ago, I said I was going to eat 6. Okay, so 14, permutation 6. Now, in terms of the formula, this means I still have that same 14 factorial on top, the whole number. But what goes on bottom is the subtraction of those 2 values. So in my example, it would have been 14 minus 6. And again, you see factorials occurring on top and bottom, so there's a very good likelihood, like as in 100%, of being able at some point to cancel something out. Okay? So we're going to do an example of one. and take a look. I first want us to make sure that we understand why it satisfies this category. It says, 30 contestants put their name in a hat for a raffle. First place wins $100, second place wins $50, and third place wins $25. In how many different ways can the prizes be awarded? Okay, so there's a couple of things. First, is it distinguishably different in terms of the items, the elements in this sample? It is, because it's different people. Okay? No two people are alike. So that has to do with the 30 contestants. They're all different people. Distinguishably different people. The first place, second place, third place, that has to do with how people are winning things. In other words, if I win first place or I win third place, I win. But I win differently, right? So the order in which we put these people in their winner's circle matters. That's why this is the permutation instead of what we're about to encounter in a moment called a combination. The order matters. I either win $100 or I win $25. That's different. Okay, everybody good so far? Okay, so this really is a permutation of unlike objects because order matters, contestants are different. All right, so this says what I should be doing then is I should be taking from all of my elements, so what is in? How many do I have for my in?
30.
That is 30. And it is a permutation. How many am I going to choose? 3. There's only 3 winners. So the other 27 people go home empty-handed. So help me fill in, what does it look like over on the right-hand side of my equation? Good.
Over 30 minus 3 factorial.
Awesome. And you don't have to write 30 minus 3 if you just want to subtract it in your head. That's cool. I'm going to write it for a while, and then at some point I'm going to stop writing it too. Okay? So I will at some point too here, even if I do write it, I'm going to have to simplify. So 27 is what I get on bottom, right? Okay, these numbers are almost the same, right? 30, 27, they're awfully close. So I'm going to take the number 30 and I'm going to write it out until I get to what? 27, and I'm going to stop. So I'm going to write 30 times 29 times 28 times 27 factorial over, I don't want to write this one out at all, right? 27 factorial. They match. It's good news. So what am I going to do with them? Cancel them out. And your calculator very quickly will be able to do 30 times 29 times 28. And you can tell me exactly how many different ways in which people could do this, win this raffle.
360.
Awesome. And that's only 30 people, isn't it? The numbers get really big here. Did you have a question, Andrew?
You know what's the point of the other side of the equation?
It's just the notation for what we're calculating. If you decided that you didn't want to write this notation down, that's totally cool. I do want you to be aware of it. Like, I can't remember if I assigned any, but sometimes I'll assign problems where it just says, calculate, and it says 30p6, and you need to know what that means. So there's really nothing going on over there. That's actually just the notation. Okay, any other questions on this one? Okay, we're going to shift gears. We still have distinguishable objects, but what we have different now is the order does not matter. So we're still having n people to choose from or n different items to choose from. We're still only choosing r of them, but now the order in which I choose them doesn't matter. Okay, so if you think about my starburst, this would be eating my starburst but not caring whether I ate red or pink first. I just know that I got a red and I got a pink. Okay? What's different in the formula? They're almost the same. There's a C. I think somebody said there's a C. There's a C here for combination. Over here. Yeah, I've got an extra thing on bottom, right? R factorial. So now think with me. Because I have this extra R factorial on bottom, will I get bigger numbers or smaller numbers? Smaller. Because I'm dividing by some more stuff than I was dividing by before, right? So I will get fewer ways in which this can happen, and that should make sense because what I'm saying is that if I got red, pink, blue, that's the same thing as getting pink, blue, red, whereas before I would have counted them as two different outcomes, right? So that's why this is happening. All right, so let's do the same example almost that we did before. 30 contestants put their name in a hat for a raffle. 3 people win $75, and how many different ways can prizes be awarded? Why in this one does the order not matter? The outcome for the winners is the same. You guys see that? Still 3 winners, still 30 people, but now it doesn't matter if their name was chosen first out of the hat or third out of the hat, they have the same prize. All right, so the notation for what I'm actually finding is 30C3. And I still have 30 factorial on top, excuse me. And I still have 30 minus 3, or 27, if you want to write that down already, factorial on bottom. But what else do I have on bottom? 3 factorial. And I do the same thing that I did before. I simplify that to 27 factorial if I didn't write it that way at the beginning already. And again, I write the 30 out till I get to 27. Nothing is any different computationally so far. But like I did on the example with my starburst, that 3 factorial doesn't identically match right now. So I'm going to go ahead and write it out as 3 times 2 times 1. Okay, so just like before, 27 factorial cancels. But now I have a 3 and a 2 to contend with to simplify with what's in the numerator. So you could do one of 2 things here. Let me maybe just say this. One thing you could do is you could just multiply the numerator, multiply the denominator, divide. You're using your calculator anyway. It's going to be a whole number. You could do that. It's not a problem, really. I mean, like, this is really going to be the same 24,000 number we got before divided by 6, right? We could do that. You could also reduce it one more step and then multiply it out, especially if you were doing it from the very beginning. It's actually quicker in the calculator if you just do the reducing, as long as you don't make a mistake in your reducing. Be careful. And so we could do the reducing. I'll show the reducing just so that you're aware of it. What is 3 times 2? 6, and I take the 6 out of the 30, I would get a 5. So that's the reducing that I'm going to do. Then we're going to multiply 5, 29, and 28. We are going to get a smaller number. What's it going to be? 4,060. All because the order of the choosing didn't make any difference.
So is that the only way to do the reducing? Like, could we do
Nope, you could do it differently.
30 divided by 3.
Uh-huh. And then 28 divided by 2, absolutely, yeah. It won't make any difference how you do the reducing. I mean, obviously if you make a mistake, it'll make a difference. But as long as it's actually divisible, then you should be just fine to reduce it however you see. Okay, what we're going to do next is we're going to do a series of different kinds of examples. I tried to show you, well, what I did show you is one example of each of these types. So after this, there's like 3 examples, I think, or something like this, where it's up to you to decide what it is you're supposed to be picking, how you're supposed to be answering the question, okay? So the first one that we're going to look at is an example of a phone number, I believe. Yep. If all phone numbers in a large business are 405767 and then 4 different last digits. That's how OBU campus is. All our numbers here are 405, and then they're 585, I think, now. I think they changed them all over finally. They're 585. So it's just the last 4 numbers that are different. The question is, then, how many different numbers are possible in this scenario? So what do you think? Permutation, combination, principle of counting, unlike object, like objects, order matters. I mean, what's going on here? It's not a permutation, but good guess. It's a fundamental principle of counting. The reason it's not a permutation is because you don't have to pick a different number every time. So like I could repeat digits. When you do permutations, you don't repeat things. So like think about our people who are being drawn for their prize. We didn't have 2 people win the same prize. We actually had to have a different person win prize number 2. At least inherent in the way we think about the problem. That's what we were assuming. So this one is a fundamental principle of counting. I like to draw sort of placeholders. You don't have to draw placeholders, but I want to think about it that way often. There's 4 numbers. How many options do I have in each blank? 10. Why do I have 10, not 9? Here's a 0. Yeah, good. All right, so I have 10 digits, 0 through 9, that are possibilities. And the fundamental principle of counting says that I would multiply these values together. What number does that give me? 10,000 is correct. Very good. So there are 10,000 numbers. 10,000 different phone numbers, in other words. You could have a very large business if you had 10,000 different extensions, right? Yes, you could. I don't think we have 10,000 extensions on campus, just so you know. Probably not. Okay, let's take a look at another one. This one actually has a couple of ways in which it can be done. So we'll take a look at both of those just to give you some kind of sense that sometimes it's not just one and only one way. A worship team practices 8 songs on Wednesday night for the Sunday service. If the worship minister plans to choose only 5 of the 8 songs practiced, in how many ways could the songs occur? Permutation would work. They're unlike objects because they're different songs.
You're only choosing some of them.
Okay, so let me do that the first way, and then if somebody else sees another one, then I'll do that one. If not, I'll show you the other one. So this is 8 songs. It is a permutation because why does the order matter? I should say that. Contextually, this is not a math question. This is a contextual question. Why does it matter? What's that?
So the band knows what's coming next.
Okay, that's part of it, right? You want to make sure they start the same song together.
The songs just go better.
There's usually a natural flow inside of a service or a concert or whatever to the order of the songs, right? There's a way in which the person puts it together that makes sense. I mean, there's a reason that we don't sing, God's Not Dead during offertory. You guys with me on that? Right? There's some sense of where you put things, the altar call. Not going to be during the altar call either. All right, so this would be where order matters. It does. All right, so this is 8P5. Okay, so somebody tell me what's going on the other side of this. 8 factorial. Okay, good. 8 factorials on top.
8 minus 5.
8 minus 5 on bottom.
Factorial.
Factorial, very good. So this is what on bottom if I subtract?
8 factorial,
3 factorial on bottom. So I have 8 times 7 times 6 times 5 times 4 times 3 factorial. I mean, it really doesn't save me a lot of steps on this one, but I'm still going to do it. My 3 factorial, just for consistency's sake. My 3 factorials will cancel, right? And somebody's going to be so kind as to get us a calculator and multiply all those numbers together on the top. 6,700 what? 20? 20? Awesome. All right, so this is orders. We'll say this way. It's song orders, but the orders of songs. Okay, did anyone see a different way this could be done? Because there is a distinctly different way that you could do. I would say distinctly different. At least a different approach. Obviously, it's not distinctly different. It wouldn't give you the same answer, right? You could do this as a fundamental principle of counting problem. I have 5 songs, right? So I'm going to draw 5 lines. How many choices do I have for song number 1? 8. Now, unlike the last problem, I'm not repeating song number 1 because when we do that in a worship service, we don't really think we change songs, right? Okay. So how many choices do I actually have for song number 2? 7. And then 4. So on this one, obviously you get the same numbers, right? I mean, it's the same numbers. And this is still 6,720. But it's thinking of it from a different perspective. Agreed? Yeah. Is my next one the card problem? Awesome. Okay, so far all we've done is counting techniques. That's what these are called, counting methods. We haven't actually done anything with the probability part of what's going on in this section, but we are very nearly about to. All right, so. Okay, cards. Have we talked about cards? We have, right? Where we said how many cards and stuff. Good. Okay, so let's kind of put those thinking caps on again about cards. We're not going to get too far into cards in this section, but we're going to do a few things. The first question wants to know how many different 5-card hands can be dealt. Okay, so the first thing we have to decide, just like on the last 2 problems, are permutation, combination, like objects, unlike objects, fundamental principle of counting. What is going on in the problem? They're not like objects. Why not? Because every card's different. Yeah, every card's different. It's not like having 2 red starbursts.
Because the order doesn't matter.
Okay, so why would the order not matter, Amy?
Because you're getting 5 cards, it doesn't matter what order you get.
Yeah. In fact, that's usually what you do when you first get your 5-card hand or whatever game it is you're playing is what do you do with your cards in your hand? You organize them in some fashion for whatever the game is, whether it's Skip Bow or Go Fish or Old Maid or Uno. I mean, you organize them in some fashion, right? So the order in which you get those cards makes no difference. So you're right. You guys got it. It's a combination. So it's a combination. That's that capital C. How many things do I have to choose from? 52. And how many am I choosing? Good. 52, choose 5. All right, I will do the hard part. 52 factorial right there on top. What's going to go on bottom? Okay, so we have 52 minus 5 and 5 factorials. This is the first one we've done where we've got something else on bottom because it's the first combination we've done, well, since our earlier example.
Why do you have an extra 5 factorial?
Because it's the combination formula. When we do combinations, if you go back to that formula, it has r factorial as part of the denominator. Okay, so somebody had already told me the subtraction. What's 52 minus 5? 47. Now this is a really good example, and when you guys are doing group work, if you have the kind of calculator that has factorials and stuff in it, I'm happy to show you where it is, and so you know and everything and can check what you'd like to check. That's cool. But your calculator cannot handle 52 factorial or 47 factorial. It turns it into scientific notation. So it might have been able to handle my 14 factorial earlier, but it very quickly gets very large, and it just can't do it. Okay? So this is a really good example of one where we absolutely have to reduce if we're going to get the right answer. Okay, so let's take a look. We're going to write out 52 until I get to what? 47. And I'm going to write my 47 factorial on bottom just as 47 factorial. But what else am I going to write on bottom?
Times 4.
You guys are getting the hang of this. You're doing great. Okay, so 47 is going away, right? And that's actually, this is the point where if you really wanted to multiply out the numerator, multiply out the denominator, let your calculator do the division, you could do that. It'd be okay. You also could reduce right here. There's some simplification that we could do if we'd like to, and do that way. So I'm kind of a fan of simplifying what I can, and then just letting the calculator multiply afterwards. That's where I tend to go, but you don't have to. So for instance, if I looked at the 5 here and the 2 here, 5 times 2 is 10, and I have a 50 right here. So I could reduce the 10 in the denominator with the 50 in the numerator to give me a 5. And maybe that's not what you see or what you want to do. That's cool. But this is the one I see when I look at it. Okay? And then I kind of do the same thing with the 4 and the 3. 4 times 3 is 12. And I have a 48 here. And what's 48 divided by 12? 4. And again, that's just one that I remember from my multiplication tables and such that just draws itself to me. I didn't mean 12 there. 4, sorry. This sort of just rings a bell when I see it. If you don't see that one, don't use it. It's not a big deal, all right? You do need to be careful, like we talked about, though, of making sure you're multiplying out all the pieces you have afterwards. So you have 52, 51, 5, 49, 4, all those multiplied. And this is a large number as well. Apparently, I was a real fan of 2 million, because it's 2 million something, right?
2,598,960, I think.
Yeah. Oh my God. It's like,
2,598,960 different hands of cards. That's a lot, isn't it?
Also your last
It
name.
is my last name. Yes. Yes. Okay. So far, so good? Now we're going to simplify the problem because what we're going to be asking ourselves is we don't want a hand of just any kind of cards. What if we really just wanted the hand that has all diamonds?
not a 15.
Okay, so there's really not 52 diamonds in a deck, right? How many are there?
13.
There's 13. So I would only have 13 to choose from. The order still doesn't matter, so it's still a combination. And I'm still choosing 5 because I want a 5-card hand. So the only thing that's different is how many I have to choose from if I really want all of them to be diamonds. Okay, so this is 13 on top, factorial. I have 13 minus 5, which is 8. So I have 8 factorial on bottom. And then I also have 5 factorial on bottom because it is a combination. So I'm going to write out 13 times 12 times 11 times 10 times 9 times 8 factorial over 8 factorial times 5 times 4 times 3 times 2 times 1. Okay, 8s are gone. 8 factorials, excuse me, are gone. What else? 5 times 2 is 10, so that's actually cancels out really clean. And 4 times 3 is 12. We don't have 2 3s, though. Yeah, we don't have 2 3s in the denominator still. We have left 13, 11, and 9. What does that give me? 1,287.
Oh.
Are you good?
You used both the 3 and the 4 for the 12. I just
I
reduced
did.
it to 3 in the top. That's
Oh,
fine.
okay. That's okay.
Yeah.
You'll get the same answer.
Yeah.
Yeah. All right. Did everybody get 1287 here? Okay, so here's where we get back to probability. Next question. What then is the probability of getting a 5-card hand of all diamonds? Okay, so I want to write out a little notation. I was thinking about this when I was putting all this together. I haven't written this out when I've taught this before, but let me write it out and see if it helps some. What we want is we want the probability of getting all diamonds. Now, I'm going to abbreviate diamonds just with the capital D, okay? So that I don't have to write as much. All diamonds. Well, if I want the probability of getting all diamonds, then that means I need the number of ways of getting all diamonds divided by the number of ways of getting any 5 cards. That's what probability is, right? The number of ways of getting what we want divided by the number of ways of getting just the luck of the draw. Okay? But I think we already found both those values, didn't we? What's the number of ways of getting all diamonds? 1,287. And what's the number of ways of getting any old 5 cards? Yes. That really long 2 million number. And if you answer the question and stop right here, it doesn't really make a lot of sense in terms of context of the problem. It really only makes sense in context of the problem if you do the division and get the decimal approximation for it. So that's what we're going to do at this point. And we're going to go with 4 decimal places on our probabilities, okay, in this section. That works pretty well with most of the values they give us. What do you get on this one? I think it's 5 if we round, isn't it?
5-0.
Okay, if I turned this into a percent, I'm not asking you to do that, but just think with me. What would I get? 0.05%. So, if you're banking on getting a hand that's all diamonds, it's not very likely, right? Very, very unlikely. And if you wanted to see, well, what if I wanted all diamonds or all hearts? Well, then you just add those two together. Still not very likely. You could do all of any suit, right? I want 5 cards of any suit. Well, we could just add this together 4 times. Not very likely. Okay, so this is a very rare thing to happen when you're playing cards. All right, let's do the same kind of thing now, but we're going to change gears. We're not going to do cards. We're going to do a committee. Now, one of the things that I did on the last problem is that I sort of didn't just give you question C. I led you into question C by doing questions A and B in advance, right? So once we got to question C, we were able to just put it together and we were done. This question looks a little bit more like some of the questions you're going to see in your homework where they just jump to question C and they're going to assume that you know what to do with the A and the B, quote unquote, that are sort of inherently needed but not asked for. So let's read through that and you'll see what I mean. We have a committee of 3 people that we're selecting at random from 7 seniors, 5 juniors, 3 sophomores. We want to know the probability that the committee consists of all seniors. So let's write it out the way I did with my probability of getting all diamonds. We want the probability of all seniors. And again, I'm going to use S just for seniors. Okay, well that means I need the number of ways of getting, and there's 3 people I'm selecting, so getting 3 seniors. That's my desired outcome divided by the number of ways of what? Of getting anybody, right? The number of ways of getting 3 of anyone. So the problem really amounts to me needing to find the number of ways that's going on the numerator and then the number of ways that's going on the denominator. The probability question of it's easy, it's just division. But it's the counting ways on the top and the bottom that are actually more difficult. So those are the two things. We'll come back to this part, but in order to do this part, we have to find the other pieces. So let's find the number of ways of getting all, well, I'll put 3 in here just to remind ourselves. We need 3 seniors, or 3S. Okay, it's a committee that consists of these 3 people. We have to decide, does the order in which we select committee members matter? No, doesn't make any difference. You're selected first, you're selected last, you're still in the committee. Okay, so which makes this a what kind of problem? Combination. So it is a combination. How many seniors are there? 7, and how many am I wanting to choose? 3. So this is 7C3. So my numerator is 7 factorial. What's in my denominator? 7 minus 3, which is 4 factorial, and 3 factorial. And if you'll notice, the cool thing about this, and it's inherent in the way the problem, of course, is defined, but the 2 numbers in the denominator, they add to the number in the numerator. You guys see that okay? That's always going to happen with combinations. All right, so we're going to write this out. 7 times 6 times 5 times 4 factorial. I've got 4 factorial on bottom. And 3 times 2. What reduces?
What if you want to?
Yes, thank you. Okay, what else reduces? 3 times 2 is 6. So how many ways are there of getting all seniors? 35. Now we need the ways of getting anybody. Any 3 people. So what do I have? 15 C3, right? Because there's 15 committee members. This isn't a comparison of seniors versus not seniors. This is seniors compared to everybody. So that's why it's all 15 people I'm selecting down here. So I have 15 factorial over what? Good. 12 factorial, 3 factorial. So I have 15 times 14 times 13 times 12 factorial over 12 factorial times 3 times 2 times 1. 12 factorials cancel. This one's probably not so nice to say 3 times 2 is 6 because that doesn't actually help my numerator. So what could I do?
You could do divide by.
Yeah, so we've got the 2 and the 14, the 3 and the 15. I heard people saying both. So 15 divided by 3 is 5. 14 divided by 2 is 7. So you actually have 5 times 7 times 13, which gives you what? 400 what?
55.
55. Those are the 2 pieces that I need to come back up here and actually answer this question now, right? So what am I going to have? 35 over 455. And what is 35 divided by 455? It is 1/13. Let's put it in a decimal form, because in terms of context, like how likely is this to happen, our minds process that a little bit better with word problems. So what would that look like with decimal approximation? 4 decimals.
0.769.
So 0.769, something like that. That's about a 7% chance, right? Almost 8%. 8% chance. So it's not real likely, but it's not like so obscure, like never going to happen, like the cards of hand problem, right? The hands of cards problem. Okay, we're going to change the problem slightly. I want you to be really careful. We've talked through some of this before, but it's really easy to get confused. This question now says, what's the probability the committee has no juniors? What's that? Sorry, I said it wrong. No seniors.
Let's just do 1 minus
35.
Okay, so let's actually answer that question first, because that's what I wanted somebody to ask me. Can't I just do 1 minus? The answer is actually no on this one. Why not?
Because the 35 is all seniors, this one wants no seniors at all.
Okay, so this problem says that they don't want seniors. It doesn't say they don't want all seniors. So if this problem just said, what's the likelihood that we don't have all seniors, then yes, we would do 1 minus it. But this specifically says I don't want any seniors. None of them get to be included instead, right? It's a very exclusive kind of description. So be really careful. There are times when that 1 minus thing is perfect, but there are times when the language just doesn't work for it too, and that's one of these times. So in terms of writing out what this is, what I want is I want the probability of, like we said, no seniors. What does that look like? I mean, what does that mean to have no seniors? It's all juniors and sophomores, right? So I need to know the number of ways of getting 3 juniors and sophomores. So I'm putting J/S, S for, how about SO for sophomores? And then I still want to know the number of ways of getting any 3 people. Well, I already know the denominator, right? Do I need to find it again? Oh, heavens no. We don't need to do the work twice. So we already got the denominator's 455. I think it was 455, right? Okay, good. So we need, still though, we do need one piece. We need the number of ways of getting 3 juniors and sophomores. All right, so how many juniors and sophomores are there? There are 8. How many am I selecting? 3. It's still a combination. So I have 8 factorial on top over what? 5 factorial. 3 factorial. Very good. So this is 8 times 7 times 6 times 5 factorial. And I'll pause. So it matches my 5 factorial on bottom. And then 3 times 2 times 1. There went the 5 factorial. What else happens? Yeah, that one worked out pretty nicely, actually. So what's 8 times 7? 56. So this is more or less likely than the seniors example. It is more likely because the numerator is higher, right? So we know this is actually more likely. And then what value do we get? What is 56 divided by 455? 3, 1? Is that what I heard? Okay, 1, 2, 3, 1. Okay. If we round. Okay. So it is slightly more likely, about a 12% chance instead of an 8% chance that we were looking at. Not quite double, but a little bit more likely than getting all seniors. Any questions on this one? Okay.